Welcome. In this session in linear data analysis, we'll explore some of the properties of the logistic function. We use this function to map the score of a data vector to the probability that it's in the positive half space of a hyperplane. When we graph this data, this is what we see. On the horizontal axis, we have the score. The score is for a unit, for any vector, any data vector. The score is the inner product of the unit vector for that hyperplane plus the bias term for that hyperplane. The vertical axis is the probability. So the score is ranging from -infinity to infinity. Here I'm truncating it to be -6 to 6. And the probability ranges from 0 to 1. And what we can see here is that this is a monotone function, and it's 1 to 1, and it's invertible. And of course there's an infinite number of functions that have this shape. This is called a sigmoid, or an S shape. And of this infinite number, the logistic function is the one that's most commonly used in machine learning, and it's also widely used in statistics. Let's observe some of the properties of it. It asymptotically approaches 1 as the score becomes very high, and the score becomes very high when the vector u that we're exploring is far away from the hyperplane. The probability asymptotically approaches 0 as that point u gets farther and farther away from the hyperplane h that we're exploring. And when the score is 0, we can see that the probability is 0.5. So now let's superimpose on this graph a plot of the Heaviside step function. So let's recall why we used that. We used that to say when the score was negative, the Heaviside function was 0. And that would correspond to this horizontal line. And when the Heaviside function was, when we take the Heaviside function of a positive score, we clamp that up at the value 1. So that would be something like this. And the Heaviside function would then take a jump like this. And so this line is our Heaviside step function, and the computer generated line is the logistic function. And we can see that in one sense the logistic function is giving us a smooth continuous approximation to the Heaviside step function. And if we were to scale this score, we could get this, that would be basically multiplying a slope. And so if we want to, we could adjust this so that it comes closer and closer to this approximation. That is seldom done in machine learning. What we usually do is we usually use either the unit normal vector for the hyperplane, or we would just use a vector w that comes out of a machine learning system. So now that we understand a few of the graphical properties, let's go through some of the mathematical properties. In particular, let's find the derivative of this logistic function. Let's work out the derivative of the logistic function where we're writing the probability as a function of the score of a vector rather than of the vector. So the probability of a score, we said, was the exponential of the score divided by 1 plus the exponential of the score. And this came because we said that the probability was the odds over 1 plus the odds, and we said that the odds are the exponential of the score. So let's observe that 1 minus the probability of the score is, we could represent this. So we have the exponential of the score over 1 plus the exponential of the score. And we could represent 1, well, in order to get this subtraction to work, what I'll do is I'll say 1 equals 1 plus e to the score over 1 plus e to the score. So 1 plus e to the score over 1 plus e to the score. Now that the denominators work, the numerators subtract, and so that is 1 plus e to the score minus e to the score is 1, and that is 1 plus e to the score. So this was our observation earlier, is that, so that equals the probability of the negative score. So we made this observation, now we're sure of it. So let's keep these in mind. And now let's recall, I know this is going to be annoying, let's recall how to take the derivative of the quotient of functions. So this is a gigantic recall, and it's been my observation in teaching that people's memory of differential calculus decays exponentially and over time, and that decay starts the moment they change from differential calculus to integral calculus. So I don't expect you to actually totally recall this. I recall it. So that is the derivative with respect, now our free variable is z, the derivative of, if I have one function over another function, the derivative of that is f prime g minus g prime f over g squared. So that is f prime g minus, let's write it as f g prime over g squared. So we'll recall that, and the only other thing we need to do is recall the derivative of the exponential, and that was one of the ones that was almost magical to us when we were taking calculus. The derivative of the exponential function is the exponential function. Well, let's put these together and try to find the derivative of the logistic function. So the derivative of the logistic function, so the derivative of the probability of a score of a vector is, now what we'll do is we'll just substitute and simplify. So f prime, so what is f? Here, f is e to the z, so that is e to the z, and what is g? That is 1 plus e to the z, 1 plus e to the z, and then minus what is f? That is e to the z, and what is g prime? What's the derivative of 1 plus e to the z? Well, that is e to the z. Okay, and then the denominator is g squared, so that is 1 plus e to the z, quantity squared. So I'll distribute this multiplication over this addition. That's what I like to do. So that is e to the z plus e to the z, e to the z, minus e to the z, e to the z, over, and I'll just leave the numerator, 1 plus e to the z quantity squared, and that equals, so this is just e to the z, right? Now, let's factor this into two pieces. So what I'll do is I'll say that that is e to the z times 1, right? So that is e to the z times 1, and then I'll take this and factor it twice. So that's 1 plus e to the z, 1 plus e to the z. And what is that? Well, that is the probability of a score. And what is 1 over 1 plus e to the z? That is 1 minus the probability. minus the probability. So if I need to compute the derivative of a logistic function, all I need to do is this computation, is I need to compute this probability, then I just multiply that probability by 1 minus that probability. I only have to do this one function evaluation, and I can very efficiently compute the derivative of a score, the derivative of the probability of the score given the score, by just doing one function evaluation, a subtraction, and a multiplication. Let's summarize our understanding of the logistic function and probability so far. Odds are a ratio that involves probability. The probability can be computed as the function of the distance of a vector from a dividing hyperplane. The logistic function is continuous, differentiable, and invertible. It's not just differentiable. We found its derivative. And there are many extensions of the use of the logistic function and of these probability ideas in machine learning and in data analytics. So, what have we learned in this lecture? Well, we're now able to transform between odds and probability. Given one of these two, we can compute the other. We can find a unit form of a hyperplane H. That is something that we learned to do in many sessions ago. And we can find the probability that a vector is on the positive side or in the positive half space of a hyperplane that's performing a binary classification.